Section 3.4, we're going to talk about algorithms for whole number multiplication and division. And the first thing we're going to start with in this section is exponents. So we're talking about a definition of exponents. You'll see how these come into play with what else is going on in this section in a little bit. But to start with is when we're going to actually just encounter just a moment ago talking about your homework. But let's do the definition of exponents first. So an exponent comes about by repeated multiplication. Okay, so multiplication came about from repeated addition, right? You add something together multiple times, it becomes multiplication because you've multiplied it together. If you multiply something together bunches of times like this, and in fact this would be n times, that's the same as writing a to the nth power. We're working with rational numbers a, and actually we're going to be working with whole numbers for the most part in chapter 3, but it actually is true for all rational numbers. And n needs to be a natural number for us to be talking about this in a way that this is going to make sense. So the first one that we talk about here is taking a to the nth power and a to the nth power. And this is the one we had actually seen just a moment ago. And what we do here is we add exponents. I'm going to talk about why all these work in just a second. But when we multiply the two bases together with the same base, we add the exponents. So take a look then at number 2. If when we multiply them, we add the exponents, what do you think happens when we divide them? You subtract them. Now, how is 3 different than 1? There's some parentheses. Yeah, there's 2 exponents, but there's only 1 base, right? I mean, that's the biggest thing, is that there's only 1 base going on. So I have an exponent raised to another exponent. When that happens, I actually end up multiplying my exponents together. And the last one, number 4, is going to look kind of like something we've given another name to. It's not the same thing, but it has a similar feel to it. It's a similar feel to distribution. We have ab to the mth power, and that can be written as a to the m times b to the m. Now notice this definition of exponents up here was defined for natural numbers n. What are natural numbers? Right. They're the ones that you naturally started to count with when you were counting numbers the first time. So you don't include 0. So the definition on the bottom of the screen is necessary because of the way we've described the very top of this. So by definition, for now, I'm going to say it's by definition, when we have a to the 0, we actually get the number 1. So anything to the power of 0 is the number 1. And in Math 2, we actually talk about why that works without it being a definition. It's not really a definition. It actually has a reason behind it. Typically in mathematics, we only define things that we can't prove. Right? We actually give you a definition for something of which to build on. You have to build upon something. So we don't really need this to be a definition when we get to Math 2. Okay? All right, so I want to talk about why these properties actually work, because these are not definitions. These actually work in mathematical sense, that I can prove them. So I told you just a moment ago that this is a to the m plus n. And this is the example that I was showing on the board. If I have a to the 3rd, that's a times a times a. And if I have a to the 4th, that's a times a times a times a. And we can quickly see that this is a to the 7th because there's 7 a's. And if you compare the 3 and the 4 to the 7, the way you get 7 out of 3 and 4 is that you add them together. So that's why this works. Concrete example. Second one. Well, you guys actually told me, and you were correct, that this is subtracting the exponents. Right? So if this is subtracting the exponents, we can show why that works by actually taking an example, a to the 4th, which would be 4 a's, over a to the 3rd, which is 3 a's. And what happens? Yeah, they reduce, right? So there's this value that we talk about canceling out, which I know you guys are comfortable with that term, but you have to be really careful sometimes when you use it, because we actually sometimes use the word cancel out, saying things that cancel out to 1. And sometimes we use the word cancel out and we mean cancel out to 0. Here we mean cancel out to 1, right? They reduce, they simplify. And we can do that with 3 of them, actually. So I'm actually left with a, and if you wrote an exponent, it would be a to the 1. And how do I get from 4 and 3 to 1? You subtract. So this is a subtraction feature. All right, number 3 said that we should be able to multiply those exponents together. So let me show you that from the perspective of what we already know. Well, we know that a cubed would be a times a times a, and all of that should be squared. But squaring something means multiplying it by itself. So this means a times a times a times a times a times a. And how many a's is that? 6, right? So how do I get from 3 and 2 to 6? Multiply. Are we good? That's how it works. Last one might be, it is a little bit different. This one is the one where we said that it sort of had this, what looked like a distribution going on. What we do on this one is we recognize that when we have that 4, we can write this as AB, kind of like I just did on the problem above, AB 4 times. Now I'm not going to show all the steps of it, but the last question that you guys asked up here, where we had to sort of verify each time we did something to change an expression into something else, when I want to actually be able to change this, I want to actually be able to sort of reverse things, right? I'd like to be able to regroup. For instance, I'd like to be able to group all the A's together and all the B's together. And I'm allowed to do that because the associative property, where I can switch things that are inside the parentheses, and I'm allowed to do it because of the commutative property, where I'm actually allowed to switch the order of things. Okay, so because I can switch the order and I can switch how things are grouped in parentheses, I can actually group all the A's together, and there are 4 of them, and all the B's together, and there are 4 of them. So I get a to the 4th, b to the 4th. So this is a combination of the associative and commutative properties that allow that to happen. Okay, I don't want you to be confused about why I just did what I did. Why I did what I did is because there's going to be some child in some class, for one of you guys, who's going to say, but why? Why do I add those exponents? Because it sure looked like I should have multiplied them. Because it kind of does, right? I mean, it looks like over here in property number 1 that we're multiplying, so why in the world do we add exponents? You should know why, okay? There's no reason that this isn't difficult, it isn't tricky. You should be able to give the child a concrete example of why it works. That's why I did those 2 slides. I did not do those 2 slides because I expect you to write things out every single time you see an exponent. I want you to use the exponent rules. That's why we've got them, okay? But we didn't just invent them and they didn't come out of nowhere. So you should have a reason back in the back of your mind, and if you had to go and look it up, that there really is a reason. These aren't definitions. There's actually a reason behind them. So when we're looking at these simplifications, I'm not going to write out 5 10s, 10 5s, 2 5s, and 4 5s, and then count up all the 5s. That's not the point. The point is to use the properties to help me out to do this. So this is all multiplication, right? So what will I do to get these to simplify? Add the exponents. So I'm going to write it out. You don't have to write this part out, but this is 10 plus 2 plus 4, which gives me what?
5 to 16.
16. Yep, 5 to the 16. So this is the answer. And you wouldn't have to necessarily show all the addition for that, but that is the process you got to get 16, right? All right, how about the next one? The next one's different. How is the next one different? Because it definitely is different. The bases do not match, do they? I've got a 6, I've got a 2, and I've got a 3. There's a couple of different things that you could do here, so I want you to tell me what you see. What could you do?
Could you add the 3 and the 2 because they have the same exponents?
You couldn't add them, but you could multiply them. Yeah, you could, and so that's definitely one approach to that. So that's the way I'll do it first, since that's the one that you mentioned, Brianna. So we could actually write this as 6 to the 4th, and then we can kind of use that 4th property in reverse. I can pluck out, if you will, that power of 3 since it's on the 2 and the 3. And 2 times 3 is 6. And now I do have the same bases. So I've got, 6 to the 4th and 6 to the 3rd, which is 6 to the 7th. That's one way to do it. Did anybody else think of something else when you saw that? There's at least one other option.
Try to get the same base.
Like how? What did you have in mind, Brina? Or Taylor?
6 is a multiple of 2 and 3.
Mm-hmm.
So can you turn 6, just change the bases?
Yeah. So I hope this is what you're saying, because this is what I'm hearing. That you'd like to take the 6 and you'd like to turn the 6 into 2 times 3. Does that sound good? Okay. So we can write this as 2 times 3, which would then be to the 4th power. I have 2 to the 3rd and 3 to the 3rd. Okay, so does this look okay so far? Is that what you had in mind? All right, so this is doing this in a different way. Now, if you take a look at that 2 times 3 to the 4th power, I could actually use property 4 and I could pull those 4s in, right? So I can write this as 2 to the 4th, 3 to the 4th, 2 to the 3rd, 3 to the 3rd. And then I can recognize that both of those match. They're both 2 to a power. So this is 2 to the 7th. And the other two are both 3 to a power. So they're 3 to the 7th. Now, it doesn't look like the same answer that I got before. It is, and there's really not one that's better than the other one. The second one we got is completely factored, so that sort of has some appeal to it. But the first one is much more concise, and so that sort of has some appeal to it as well. Either of those would be completely correct solutions to this particular problem. And you're using the same properties, but you're using them in a different way, aren't you? Yeah, so that's kind of cool. It's a different way to do it, different way to think about it. All right, we're going to sort of change gears now. We're going to talk about some multiplication algorithms specifically. So some of these you've seen before probably, and some of them you probably haven't. So the first one I'm going to show you is an expanded standard algorithm. And let me do the standard algorithm first, and then I'll show you where the expanded part comes into play. So think back to when you first learned to multiply and walk me through what you did. 8 times 2, which gives you 16. So what do I do with the number 16?
Put the 6 below the 2 and then carry the 1.
Okay. Why did we do that?
Because the 1's in the 10th place.
Right. The number 16 is 1, 10, and 6 ones. So I wrote the 6 in the ones column, and I wrote the 1 in the tens column. That's important to realize. Okay. Now what?
You add the 1 with the 4.
Not yet.
4 times 2.
First we do 4 times 2.
Oh, yeah.
Yeah, so 4 times 2, which would give me 8, and then I add my 1, which is 9. Now let me point out 2 things that we just did that were a little bit complicated, and you didn't notice they were complicated because you've been doing this now for a while. One thing that was complicated is that we did a carrying sort of thing in the middle of it, and it sort of looks like a trick unless you do what I did, which is where I was saying, why are we moving that 1 over there, right? The second thing that we did is in the middle of a multiplication problem, we added. And that's a little bit weird too. Do you guys feel that? It's a little awkward to be doing an operation in the middle of doing some other operation. A little awkward. All right, what do we do next?
0.
And there is awkward moment number 3. Why in the world did we put a 0 there?
You're multiplying the 3, which is in the 10th place.
Yeah.
So you have to have a 4.
We're about to multiply the number 3, but the number 3 is not really the number 3. It's the number 30. When I multiply by the number 30, I'm going to get that 0 there. Okay? But again, if we didn't really talk about it, it looks sort of like magic. I remember sitting on the school bus in 3rd grade, and we didn't ride the school bus very often, and I remember a child older than me asking what happened if you multiplied 13 by 13 or something like that. And you don't do 13s tables, at least we didn't. So I was trying to do this sort of a multiplication in my head, and I couldn't figure out how to make it work because I didn't understand putting a 0 somewhere. We hadn't done that yet, right? That was 4th grade at the time, and we hadn't gotten to it yet or whatever. So this idea of putting that 0 in is not intuitive. That's something you definitely have to describe what you're doing and why. All right, so after that, 3. Now we're going to take the 3, and what are we going to do, Taylor? All right, so what's 3 times 8? 24. So we're going to write the 4 down, and we're going to carry the 2, and we're going to have to be really careful because now I had a 1 there that I just changed to a 2. So you got to be careful again, right? Because I originally had a different number there that I just changed. All right, and then we're going to do 3 times 4 and get 12 plus 2. And unfortunately, we're still not done, right? Because the very end of this problem also has addition going on. All right, so we'll add, again, normally if you were doing this back in the day, you added from right to left, which is not how you read, but so you would have written a 6 here. 9 plus 4 is, and you would have carried the 1, and then 1 plus 4 and 1. So your answer is 1536. So every problem that we do, there's absolutely no reason you shouldn't be able to get your answer right because you know the standard algorithm. You guys have used it for quite some time. You also have calculator and you can verify. So in all these other methods that I'm about to show you, the method should not mess you up in getting the correct answer. If anything, because you know other ways of getting the correct answer, you should be able to verify that new method that you just learned. Okay? All right, so we actually haven't finished this one. This was the standard algorithm. I want to show you what it looks like in expanded form. Okay? Because this is supposed to be the expanded standard algorithm. Expanded form looks like this. Instead of having the number 48 written as 48, we actually write it as 40 plus 8. And same thing for the 30. We write it as 30 plus 2. And then what we do is we actually multiply each of these together. And there's multiple ways to write this out. I'm going to write it out here to the side. So basically we're going to do 8 times 2, and we're going to get 16. And we're going to multiply, because there's 4 numbers here. So then we're going to multiply the 2 times the 40. So what's 2 times 40? 80. And then we're going to multiply the 30 times the 8. And we're going to get 240, good. And the last one we're going to do is we're going to multiply 30 times 40, and we're going to get 1,200, yeah, 1,200. And then, just like in the standard algorithm, the way we did before, we do add this up. But we've got 4 things we're adding up. But we get a lot of zeros in there, so it's not like it's a complicated 4 things to add up. Again, we can move from right to left if you'd like. We can do the 6 here. 8, 1, and 4 gives me the same 3, well, 13. Carry my 1 to give me the 1536. What we're doing is we're isolating the multiplication from the addition. And we're actually giving reason for why all those zeros are there, because we actually multiplied two-digit numbers 30 times 40. That's where they came from. So this is the expanded algorithm. The next one is called the partial products algorithm. And this one is for those of your kids who are visual learners. I would have loved this one. I'm a visual person. I mean, I can do, give me a list of steps and do them. That's fine. I can do that. But the visual things really appeal to me. And some of your kids, it's not just they appeal to them. That's really the only way they can process things, too. I have a brother-in-law who is brilliant. He's a doctor now. But you know how he remembers the code for the house? He looks at the keypad and he knows where he's going to hit on the keypad by looking at the keypad. That's how he thinks about it. He's a visual person, too. So when you're doing this partial products algorithm, it's going to feel somewhat like this one over here. We're going to break the numbers into 48 and 30 and 2. So what we're going to do, though, is we're going to write them in a visual way. So this is 40, and oops, that was supposed to be 8. And then this is a 30 and a 2. And the reason I'm writing them where I'm writing them is because we're actually going to draw a picture. The picture that we're going to draw is a picture that has as many boxes, basically, as we need. In our situation, we only need 4 boxes because we have 2 two-digit numbers. If I were doing a 2-digit number and a 3-digit number, then I'd need 3 rows and 2 columns, right? You have rows and columns based on how big the numbers are. So you can actually do this with very large numbers. It's just going to make a big grid when you're done. And inside of each of the boxes on the grid actually goes the numbers that we just got on the previous screen. It's the multiplication parts. So we do 40 times 30. You can fill in the boxes in any order, which is also kind of nice for those of you who are free spirits, right? You don't have to have any order to what you're doing. So 40 times 30 would be the 1200. The 8 times the 30 is the 240. 40 times 2 is 80, and then 8 times 2 is 16. So we can fill them in any order, and then we add them to, we add all the boxes together when we're done. So it's not really any different than the last one in terms of the mathematics that are being done. It just has this wonderful visual, whoops, sorry about that, this wonderful visual component to what you're seeing. So this is 1536, right? What do you think? The other thing that this does is this very, very nicely corresponds to what you mean when you talk about area corresponding to multiplication. Now, there's not a situation on this particular one where I drew it well, but let me actually draw what's really happening in terms of an area diagram. If you really had 48 and 32, it really looks something like this. This is 40, and this is 8, and this is 30, and this is 2. Like a garden, right? That top left-hand corner is 40 by 30. That's how big that plot is of the garden. The top right-hand corner is an 8 by 30 plot of land. And so forth for the other two. So there's actually, like we could actually put dimension to what we're doing and talk about it then in an application sense, and it makes perfect sense because we've already described multiplication in this way. Do you have a question? Yeah.
Yeah, what would the box look like if you were doing like a 3-digit number times 32?
Sure. So if you had like 483 times 32, right? What you would do is you would have 3 wide. We'll do it that way. And 2 long. So this would be 483, and then 32. So you have a 6 by 6. And could you do a 3 by 3? Sure. You'd end up with 9 boxes. You have 3 columns and 3 rows. So you can just expand the picture as far as you need to get all the dimension in there. You ready to take a look at the next one? Okay, so my daughter learned how to do multiplication last year. She was in 3rd grade. And they didn't do long multiplication or multiplication like this until it was the beginning of the school year maybe, so in the fall. And she was really struggling with the standard algorithm. And my daughter's not dumb. You guys know that, right? She's very bright. But it just doesn't make sense to her. She wasn't connecting why she was doing certain steps, and she was really struggling. And so this is one of those things where it's wonderful when your kid actually asks you something that you can explain to them in a different way. And you will have that opportunity with where you guys go and teach. Some kids are not going to like some method, and you're going to have to put your own preferences aside, because I will tell you, I will probably always multiply with standard algorithm. That's how I learned it. I will probably always do it that way. But just because that's what I would do doesn't mean that's necessarily what my daughter needs. The next method's the one that actually made sense to her. So this is called the lattice algorithm, okay? And you've seen the lattice algorithm for addition. We did that back in section 2. Well, we've got a lattice algorithm for multiplication. It kind of starts out looking like the last one. And it is a very visual method as well. We've got a box, and the box has as many columns and rows as there are numbers. So I've got a 2 by 2 box here. Instead of writing 40 and 8 along the top, I write 4 and 8. And for 32, I write the 3 and the 2. Everybody good so far? You really do need to write them on the top and on the right. So you can't write the 32 on the left. You could have for the partial products algorithm, that would have been fine. But you really need to write them on the left because of on the right, because of what we're about to do, where it's going to take up some space on the left. The next thing you're going to do is you're going to break each of the boxes in a half along a diagonal. And you're going to do them much like we did before. Okay, we did that before when we did the lattice ones. What you're going to do in each of the boxes is you're going to do the multiplication facts, okay? So the nice thing about this, and this is actually kind of true in the last one too, is that all of this reduces to the multiplication kids know from flashcards, right? It's all 1 digit by 1 digit multiplication. You don't even need the 10s tables and the 11s tables and the 12s tables that they teach people nowadays. No need. Okay, so 4 times 3, I tend to move across the top. 4 times 3, 12. We write the 10s digit in the top corner and the 1s digit in the bottom corner. 8 times 3, 24. Yeah, 24 on this one. 4 times 2, 8. So that's a single digit number. We only need the 1s column, or the 1s corner. And then 8 times 2, which is the one you were doing for me, Brenna, 16. There you go. And then what we do is we do like what we did with the algorithm for lattice addition, is we add along the diagonals. And we do need to start in the bottom diagonal. This part does actually put a little bit of structure on it. So the bottom diagonal is simply 6. The second diagonal here is 4 plus 1 plus 8, which is 13. So I write the 3 down and I carry the 1 to the next column. And I'm carrying the 1 for the exact same reason, right? The number 13 is 3 1s, right? And 1 10. So the 1 10 moves over. 1 plus 2 is 5, and then 1 up here in the other corner. The answer to the problem is right here. And for whatever reason, my daughter felt like that made sense to her. She really liked that method. So that's the one that she will use. Any questions on that one? Okay. The next thing is division algorithms. Let me do the slides in the other order. Let's actually start. I know I'm going to make you switch a page over, but go ahead and switch to the next page. Let's do the standard algorithm first, because that's the one you guys know anyway. And then I think I'll be able to use that to justify the other one a little bit better. All right, the standard algorithm is 620 divided by 5. That's what we're going to do. So what do we do with the standard algorithm for finding the answer? What's my first step? Right. So we look at the number on the outside, and we look at the first number underneath, and we say, how many times does 5 go into 6? And it goes into it 1 time. Then what do we do? Not yet.
Same with 5 times 5 goes into 2.
Not yet.
Multiply 1.
Multiply. Yeah, I need to do that first. Okay. So the 1 times 5 is 5, and then I would subtract, which gives me a 1. And then what?
Bring down your 2.
Bring down the 2. Now what?
Times 5.
How many times 5 goes into, so how many times does 5 go into 12? 2. And then
Multiply 2 and 5.
2 times 5 is?
10.
And then subtract. Last step. Bring down the 0. 5 goes into 20 how many times? 4. 5 times 4 is 20. And at least on this one, we're left with no remainder. We could have a remainder here when we're working with this too, but we don't on this particular one. So the answer is 124. There aren't very many methods for division. This is not a terribly uncomfortable problem. The only part of this problem that becomes a little bit difficult is when the number on the outside is not a single digit number. Right? With the single digit numbers, it's really nice because you know the multiplication tables, and your kids should too. They shouldn't be working with division until they've really kind of mastered the idea of multiplication, right? I mean, there's an order to what's going on here. It matters. So this is a good method when we're dividing by something that we know multiplication tables for. But what if we're dividing by the number 26? It's a little bit harder, isn't it? Because I don't always know how many times 26 goes into something. And in the middle of doing it, we might make a mistake and have to try another number, right? That happens. So in those cases, this other method is another option. Now, I will tell you from the get-go, it is a more cumbersome process, okay? It takes longer. This is called repeated subtraction, and you've actually seen that we had a repeated subtraction model back in the last section. Remember that? It was one of the models that we wrote down and you guys worked through last time. All right, so here's the way that this works when you have a larger value. We did it with a much smaller value last time. We actually look at the 5, and we actually say, well, I want to do 5 into 620. And so I take the number 5, and I look at multiples of 5 in terms of 10. So I have 5s, 50s, 500s, 5,000s, and so forth. I just have lots of options with 5s and 0s in the end. And what I'm going to do is I'm going to subtract. So I'm going to take my 620, and I'm going to subtract the largest one of those that I can, which is what in this problem? 500. I'm going to show you how this gets your answer in a minute, but just bear with me, okay? So if I do 620 minus 500, what do I get? 120. Okay, so the only things I'm allowed to subtract are these 5 times the power of 10 is what these are. Whatever the number is times the power of 10. So what's the next value that I would subtract? 50. And I would get 70. Good. And then what would I subtract? 50 again. And I would get 20. Now what would I subtract? 5. And I would get, and then 5 again to give me 10. 5 again gives me what? 5. And my last and final 5 gives me 0. So we get down to a number where we can't subtract anything else. 0 obviously would work, but if we had a remainder in this problem, it might end up being a 2 down there or something, and that would be okay. We can't subtract 5 again and get a positive number. So how do we get the answer? Because all that looks great. I just did a whole bunch of subtraction, but what's the answer? Well, if you take a look right here, this was 5 times 100. This is 5 times 10. 5 times 10. This is 5 times 1, 5 times 1, 5 times 1, and finally down there, I know I'm pointing sort of at the 0, but I'm not trying to, is 5 times 1. The answer is this sum. 100 plus 10 plus 10 plus 1 plus 1 plus 1 plus 1. That's the answer. It's 124. So I have 1 100, 2 10s, and four 1s. Okay? The point when this would be very not friendly is what if it went in 9 times? Right? I mean, you don't want to subtract something, the same thing, 9 times. It's not especially friendly. But this is what repeated subtraction looks like. Let's see, where does that put us? We're going to stop right there.